Welcome to the deep dive. We sift through the research so you don't have to, giving you the core insights. Today, we're diving into some really interesting foundational work on autonomous software agents. It's about a new system called ScaleCUA. The goal here seems to be pushing the boundaries for open source computer use agents, or CUAs.
That's right. And it tackles a really fundamental problem in the field. For a long time, building CUAs that can reliably handle complex graphical interfaces, GUIs, it's been tough. We know these agents need a lot of specific knowledge about software, how it works, what interfaces look like, but getting the right kind of training data, that's the bottleneck. High-quality data, especially these detailed step-by-step trajectories of someone actually using the software, it's just really scarce and expensive to collect. That's seriously held back progress.
Okay, so data scarcity is the big wall they ran into. And the mission for this ScaleCUA project was essentially to find a way around that wall, right? To build a huge training data set that works across different platforms, and then use that data to build some powerful new foundation models. So let's start with the data pipeline. How did they manage to gather quality data at such a massive scale?
The pipeline. That's really the core innovation here. They call it the cross-platform interactive data pipeline. And it's not just, logging clicks. It's a pretty sophisticated system with two interconnected loops. These loops work together to get both quantity and quality.
Two loops. Okay, tell us about that dual approach. Why not just one big data collection effort?
Well, the first loop is the agent environment interaction loop. Think of this as the automated workhorse. You have automated agents just interacting constantly with all sorts of different GUI environments, clicking, typing, exploring. This generates a huge amount of raw trajectory data and screen captures.
Okay, so that gets you the sheer volume. But raw automated data can be messy, I imagine.
Exactly. It can be noisy, contain errors, maybe the agent gets stuck or does something nonsensical. That's where the second loop is crucial, the agent-human hybrid data acquisition loop. This loop integrates that raw automated data with high-quality trajectories annotated by human experts. So the automation provides the scale and explores lots of possibilities, but the human input corrects errors, refines tasks, and ensures the data actually reflects useful, goal-oriented behavior. It's this hybrid approach that gives you both coverage and accuracy.
And the cross-platform part is pretty ambitious. They didn't just focus on, say, Windows or web.
No, they really went for breadth. The pipeline covers Windows, macOS, Linux, Android, iOS, and web environments. 6 major platforms. Just getting agents to run and capture data consistently across all those different ecosystems is a significant engineering challenge in itself.
Right. That immediately makes me wonder about controlling the agent. Clicking a button looks different technically on a desktop versus tapping on a phone screen. How did they handle that variation? How do you make an agent's actions consistent?
That required a clever abstraction layer. They designed what they call a unified action space. This basically gives the agent a standard set of commands it can issue, regardless of the underlying operating system. It includes universal actions that apply everywhere, like click, write, wait, and terminate.
The basics?
The basics, yes. But crucially, it also incorporates platform-specific actions that are necessary for real-world use. Things like long press, which you need all the time on mobile, or using hotkeys for efficiency on desktop and web apps. This unified space is what allows them to train a single policy that can generalize, or at least transfer knowledge, across all these very different environments. It's kind of the glue holding it all together.
Okay, so this sophisticated pipeline running across 6 platforms using this unified action space that generated the ScaleCUA data corpus.
Oh.
Let's talk about the data set itself. You mentioned it's designed to be open and diverse. What's the scale like, and how is it structured?
It's substantial. And importantly, it's structured to support the different kinds of tasks a CUA needs to perform. First, there's GUI understanding. This is about basic perception. Can the agent understand what it's seeing on the screen? For this, they gathered about 471,000 examples. This covers things like describing specific regions, reading text with OCR, understanding the layout, essentially making sense of the visual input.
So that's the seeing part. Then comes connecting language to those visuals.
Precisely. That's GUI grounding. This task is about mapping instructions, usually in natural language, to specific areas or elements on the screen. This is where the scale really ramps up over 17.1 million training samples here. This huge volume is needed to train the model to accurately locate UI elements. Figure exactly where to click or type based on an instruction.
17.1 million, wow. And the final piece is actually doing things, following steps.
Right. Task completion, this involves sequences of actions or trajectories to achieve a goal. They collect around 19,000 trajectories in total for this.
Now, you mentioned a distinction within those trajectories in the outline, weak semantic versus high-level goal-directed. What's the difference there? 15,000 versus 4,000.
Yeah, that's an important distinction reflecting the data sources. The 15,000 plus weak semantic trajectories mostly come from that automated agent environment loop. They show sequences of actions, but the connection to a clear high-level goal might be a bit noisy, or the actions themselves might not be optimal. They provide breadth. The 4,000 human-curated high-level goal-directed trajectories are different. These come from the hybrid loop, often involving expert refinement. These are higher quality, explicitly linked to a specific task goal, and represent more robust strategies. They average about 9 steps each. This mix gives the model both volume to learn patterns and high-quality examples to learn effective strategies.
Okay, that makes sense. So the data is comprehensive. Now let's talk about the agents they built using this data. The ScaleCU models, they're based on the Qwen 2.5 VL vision language model, which is already quite powerful. And it seems they unified everything seeing, reasoning, acting into one model. But what I found interesting was the flexibility they support 3 different ways the model can operate, or inference paradigms.
Yes, that flexibility is key. It lets you choose the right mode for the job, balancing accuracy and computational cost. First, there's grounding mode. Here, the model acts like a specialist. Its only job is to precisely locate UI elements based on an instruction. It outputs coordinates, bounding boxes, that sort of thing. You'd use this, for example, if you had a separate, maybe more powerful reasoning module planning the steps,
Yeah.
and you just need ScaleCUA to handle the visual grounding part.
Ah, I see. So it's like a dedicated visual expert component.
Exactly. Then you have the self-contained modes. The second one is direct action mode. This one's built for speed and efficiency. It takes the input, the screen, the goal, and directly outputs the low-level action to execute, plus maybe a very short description of what it's doing. It skips any explicit intermediate reasoning steps to save time and computational resources. It just acts.
The fast path and the third mode, the one that takes its time.
That's reasoned action mode. This mode explicitly generates a chain of thought reasoning process before it decides on the action. You'll often see this reasoning wrapped in special tags, like think tags in the output. It lays out its understanding of the situation, the goal, and its plan. This makes the process more interpretable, and as the results show, often more accurate, especially for complex tasks. But, as you said, it takes more computation because it's generating more text, more tokens.
That trade-off is always there, isn't it? Speed versus deliberation. Did they quantify the benefit of that extra reasoning step? Was reasoned action mode significantly better?
They did look into that specifically. The diagnostics showed a clear advantage for the reasoned action mode in terms of task success rates. They found it consistently outperformed direct action mode, with performance gains up to about 8.2 absolute percentage points. And this difference was most noticeable on the really challenging benchmarks, like Web Arena Lite v2, which involved navigating complex websites, filling forms, multi-step processes. It suggests that for tasks needing careful planning, that explicit reasoning step really pays off.
Okay, that leads us nicely into the overall performance. This is where the rubber meets the road. Did this whole data scaling approach actually lead to state-of-the-art results? What did the benchmarks show?
The results were pretty compelling across the board, looking at those 3 core capabilities. For GUI understanding, they tested on MMBench-GUI, specifically the L1-Hard subset, which is known for being quite difficult. It tests fine-grained visual details and understanding context in UIs. Their largest model, ScaleCUA 32B, scored 94.4% on this, which, according to their paper, was higher than any other open-source or proprietary model they compared against.
94.4% is very strong. And did that visual understanding translate well into locating elements, the grounding tasks?
It seems so. On the GUI grounding benchmark, ScreenSpot v2, the same ScaleCUA 32B model achieved an average score of 94.7%. This really validates that the dual-loop data pipeline was effective in generating data that leads to robust UI element localization across different platforms.
But the ultimate test for a CUA is putting it all together, right? End-to-end task completion in a complex environment where one mistake can derail the whole thing. How did ScaleCUA fare there?
That's where the results were perhaps most striking. They used the end-to-end task completion benchmark, Web Arena Lite v2. This involves tasks like booking flights, managing emails, online shopping, within a limit of 50 steps. The native ScaleCUA 32B model, running end-to-end, achieved a 47.4% task success rate. Now, 47.4% might not sound perfect, but you have to compare it to the baseline. The best native baseline they cited, UiTAR 72B DPO, only got 21.4%. So ScaleCUA achieved a gain of plus 26 percentage points. That's a huge leap.
Wow, yeah, 26 points is not incremental. That's a significant jump in capability, especially for an open source model operating directly on complex web tasks. That really speaks to the power of the scaled cross-platform data approach.
Absolutely. And they also analyzed how performance scaled with data size. They found that, generally, more data led to better performance across all benchmarks, which you'd expect. But the gains tended to follow the logarithmic curve, diminishing returns after a certain point. However, the Web Arena Lite benchmark, the most complex one, showed the most sensitivity to data scale. Performance kept climbing more steeply with more data compared to the other tasks. This suggests these really complex multi-step real-world tasks are the ones that benefit most from massive data sets and likely still have room to improve with even more data. So, to kind of wrap up the core achievement here, ScaleCUA really provides a new foundation. By creating this massive cross-platform data set, ScaleCUA data, and standardizing the action space, they've significantly advanced how we can train and evaluate these computer use agents, particularly in the open source space. They tackle that data scarcity problem head on.
It definitely provides a strong base and a clear demonstration of what data scaling can do. But they do mention a limitation, which points towards future work. They describe the current memory system as quite basic, essentially just treating past actors as a flat list, a simple history. So thinking ahead, if these agents are going to handle even longer, more complex tasks across different applications, how critical will it be to develop a more sophisticated memory? Something lightweight maybe, but effective at capturing temporal dependencies, understanding how actions relate to each other over time. That seems like the next big challenge this work sets up for the field to explore.